Alright, well thanks to everyone who's joined us for our second online clinic for 2014. With this online clinic, we're going to be looking first of all at Simply Motion, which is delivered with Solid Edge, and it's basically what it says it is. It's a tool to do quite complex animations within Solid Edge, and it's even got interference checking and things like that. Then we'll be starting to use what's called Dynamic Design and Motion Pro. Now this is an add-on for Solid Edge, but it's an incredibly powerful tool, and it also has interfaces with Solid Edge Simulation to allow full dynamic motion analysis of your assembly, and then you can take a snapshot of those loads and transfer them back into Solid Edge Simulation. So that's what we'll be looking at today. So we'll open up a model that I've got here in Solid Edge, and this is at the moment just the Simply Motion is switched on, not the full dynamic designer. Now you'll see here I've got a crane, I've got a base arm, hydraulic ram, a support arm, a main arm, what I'm calling a rope, which is actually solid, and a load. Now all of this is fairly simple. Where possible, I've got the parts constrained together. For example, you can see, I've got various axial lines and planar lines. On this joint here, it's a rather difficult joint to constrain, so at the moment I've just left it unconstrained. And what I'm going to do is I'm going to switch over to Simply Motion and show you some of the tools here. Now when you start a Simply Motion, when you first switch into Simply Motion, it creates a new mechanism and asks you whether you want to automatically add new parts to grounded or moving parts. It does this, gives you a dialog box based on the constraints that are on these parts in the assembly. You can see the base there is already grounded. It also brings across connection types relevant to the mates that you've got in the assembly. So I've got a revolute joint there. I'll expand out the joints. I've got an axial line in the ram. I've got another axial line on the top joint. I've got a planar and a few revolutes. Okay, now these cover the different aspects that I want to look at. However, like I said, at the moment I don't have any joints on here, and I want to set up some fairly special joints. They're called spherical joints, and I'll just zoom in. I want a spherical joint between that component and that component. Then it asks you for the location and the direction. Now the direction is important because this defines the z-axis on the joint. Now at the moment this is a full spherical joint. It can rotate in all degrees of freedom. What I want to do, however, is I want to constrain it so it cannot rotate about this axis, basically. Now in this case that is the y-axis, and instead of the y-axis being free, I'm just going to set that to be a constant at 0. And you can see there's a depiction in the graphic to show that I'm now constraining or driving the motion in that direction. So that's my first spherical. I've got to set up another spherical joint. You can work either from the toolbar or from the Pathfinder. Again, I'll set that to be the location. That's my direction. And in this case, I'll actually allow it to be free in all directions, more to simulate a sort of rope style attachment. Now, I want this crane to actually operate. Now, there's two things that would cause it to operate. One is the hydraulic ram would be running, and the other is there would be a drive at the base of this shaft in a rotational manner. Now on the support I've got, you can see when I move over Revolute 2, the bottom Revolute joint highlights, and if I go into the properties there, because it's a Revolute, it's only free to rotate on Z. Now what I can do is I can constrain the motion. Instead of it being free, I'm going to predefine the motion of this joint, and I'll do it as a step. I'll start at 0 and I'll rotate by 20 degrees. My start time for the rotation I'll set to be 0.25 of a second, and I'll set the end time of that to be 0.75 seconds. Now the reason I do this is because I need to actually lift this ram first, so I'm giving myself a little bit of time in order to do that before that happens. Now axial 297, you can see it highlight in the tree, in the graphic window. I go into my properties. Instead of free on the translate Z, I'm going to have a displacement, and again I'm going to use a step function. Now axials, if you want to extend an axial, it's a negative distance, and this I want to start at 0 and end at half a second. Okay, now how long is my simulation going for? Well, if I have a look in my builder, I've got various options, including units, which direction gravity is, negative Z is correct, so I'll leave that, which parts are moving, grounded, all that kind of stuff. I can edit any of my joints. I can add springs, which can be quite important in motion. With this particular case it's not, but you can add both torsional and translational springs to your assemblies as well, and that is a really key aspect of Simply Motion. Now I can also control my motion, and I've already set that up. Then I get to my simulation. In this case I want, for example, 2 seconds, and I might want 1,000 frames. The reason I have a high number of frames is to give me good accuracy during my simulation. So I'll close that off. Then I will actually perform this simulation. This is where it goes and calculates all of the loads. And you can see it's swinging around at the bottom after it's been lifted. If I just rotate that round, we can play that again. Lifts, drags behind as it starts to rotate, and then it swings back out to the other side and back again. So it's quite a reasonable simulation, and gives you the ability to create very, very accurate AVI files, including the option of springs as well. So that's some of the power of Simply Motion. Next, what we're going to do is we're actually going to shut down Solid Edge so I can turn on Dynamic Design and Motion, and then I will continue with this same model. So just give me a second. I'll just shut down Solid Edge and use the Dynamic Design and Motion Pro toggle. That just allows me to switch full Dynamic Design and Motion back on, and then I'll reopen Solid Edge. Right, now we're set up for the full Dynamic Design and Motion Pro. I've just opened a slightly different file. This one is called Crane Setup. The reason it's called Crane Setup is because I've got a simulation partially set up and ready to go. Now I'll just switch using the same button into Dynamic Design and Motion, and it's almost the same except it's got some additional tools. Now the first lot of tools that are additional in Dynamic Design and Motion Pro is I have contact, and I can have point to curve contact, curve, or full 3D part contact. I also have couplers for things like gears and bearings, and I have motion. This allows me to set motion on a particular part that is not yet constrained or even doesn't have a joint associated with it. Now, there's a key difference between contact and couplers, and that is that if I, for example, want to work out the backlash in an assembly that has gears, then I would use contact. If I just want those gears to rotate locked to each other, then I would use a coupler. Now, I'll move on to the next area. In the Simply Motion, you saw that I had springs, both torsional and rotational. That's still there, except now I have the addition of dampers, torsional and rotational, bushings. I also have action-only forces and moments, and action-reaction forces and moments, as well as impact forces. Now this gives me a whole raft more options when I'm generating motions. One of the other things is, we'll have a look at this, I think it's the Revolute joint, and the properties in that. Whereas before, if I went in Simply Motion, if I went down to expression, the expression was uneditable. Now I can actually combine various different expressions to build up a full range of motion over time. So that's another very powerful tool within Dynamic Design and Motion Pro. So we'll just have a look, and I'll just simulate this first of all and just get the simulation as we were wanting. Now this one, the rotation goes the other way. That's okay. It gives us a nice visual because we can see very clearly as the load reaches its furthest point before it starts swinging back. And what we want to do now, and this is another thing that Simply Motion just doesn't have, is I can actually look at the forces, loads, and movement of the particular parts. For example, I might want to plot the load or the position of the center of mass, and I can plot it, in the X, the Y, or the Z. I can also plot the velocity, for example, the magnitude of velocity, or the acceleration. Now acceleration has to do with forces a lot more. So I'll plot the center of magnitude, the center of mass acceleration of that load. And you can see the various accelerations that this body is experiencing. Now, one additional tool is as I scroll through my motion, I can see I can see in my graph over here, the red line indicates the current position in my motion. So you can see that the load has a peak acceleration as this body starts rotating. The rest of the accelerations are not that high. So I'll just hide that plot for the moment. And what I'm really interested in, for example, is whether or not this crane is sufficiently strong enough to allow that speed of rotation. And what I'm worried about is I'm worried that this shaft is actually basically going to twist off. So what I want to do is I want to have a look at the Revolute joint, and what I want to know is the magnitude of force, or the magnitude of the moment in the Z direction that this crane needs to survive. Now you'll see I've got various magnitudes, and I've got two or three particular spikes. So let's go back and work out what these spikes are. As we come to the first spike, it's where the revolve starts to happen. As I come to the second spike, it's where the hydraulic ram reaches the top of its lift. And I can't help but wonder if that particular spike there is because it was rising quite rapidly. All of a sudden it stops rising, and just maybe you get a little bit of a sort of, it rises a bit further and then sinks back onto the ram. So that could be the cause of that spike. Then you've got another spike as it stops rotating. And then when it reaches the full length of the swing there, you've got a peak downward force. Now the peak upward force is 137,000 newtons per millimetre, or 137 newton meters. The peak in the opposite direction is 153 newton meters. So that is really the highest point in the rotational torque that this support is going to see. This leads us to the next very, very powerful tool in Dynamic Design and Motion Pro, and that is, you can see this collector here. It shows you the active studies and the parts that are used in that active study. And what I can simply do is I can simply right click and add the loads from this dynamic simulation into the solid edge simulation. So I've added those loads to the arm, and I'll add those loads to the support. Because there's existing loads, it says do you want to add or delete. So I want to add them as well. Now I'm just going to switch back to our simulation and have a look at this. You can see that there's quite a number of loads and moments that have been added here. Now I have not added into my simulation the hydraulic ram, so I want the forces from Dynamic Design and Motion to go in there. I have not got the hook, so I want the forces there. But I do have both of these parts and the base in my well, not the base, but I've got a constraint in my simulation. So I don't actually need those particular forces in this simulation. So I can just very simply delete the additional forces that I don't need. So now I'm left with just the forces from the Dynamic Design and Motion simulation into my model. My mesh will update, and I've got a bolt connection between here to simulate that as well. All I need to do now is solve. It will load the geometry. If needed, it will remesh, and then it will apply the loads from our Dynamic Design and Motion, which are dynamic loads, and it will apply that into this static simulation and give us the results of how stressed this model will be under that dynamic load case. And we'll see the results in just a second or so. And this is a particularly powerful tool because it extends the simulation capability by working out the dynamic load cases for you. So I'll just turn off the parts that we don't need to see. And this is a highly distorted model. It's not the actual distortion. I can switch back to the actual distortion there, and I'll just turn off the loads for a clearer view, and I'll animate this. And you can see that as it's loading up, it's causing quite a large twisting and a quite large stress around the exterior of that shaft there. And I would even go as far as to say, looking at the stresses here, 580 megapascals, when the yield stress is clearly indicated at 262, that this will fail under that dynamic load case. While it's perfectly okay for the static load case, we need to put some limitations on the dynamic use of this crane. For example, we might want to put some limitations on the rotational speed of this. So if we want to do a check, then we can come back, edit the revolute joint, and we can change the duration, hence changing the speed, and we can then iterate that analysis to give us exactly the results you're looking for. So this has just been a quick example of how to utilize either Simply Motion for animations or full dynamic design in motion to combine into your solid edge scenario to just increase the power of solid edge as you go. So thank you very much for watching. Our next clinic will be on solid edge simulation, sort of a basic how-to guide. It will be on the 27th of March 2014, and if you've got any questions about this webinar, by all means review it online at the Edge PLM YouTube channel, or you can email support@edgeplm.com.au or sales@edgeplm.com.au if it's regarding sales. And if you're in maintenance, you can always ring our hotline on 1300 883 653. Thank you very much.